think we'll get started. Hey everyone, I'm Kyle Sammon. I'm a system architect at Connectivity, and today I'm going to walk through some simulations we've been running through to try to prove or see how the existing OCP interconnect works in Gen 6 channels. So a quick overview of what is in this presentation. So we're going to go through a case study of kind of thousands of different channels we've run through using the existing OCP NIC interconnect, which is currently defined by SFF TA 1002. I'll walk through a little bit about our simulation and methodology of how we simulated all these different channels, and then go through some of the high-level results and then our takeaways. And just as Damien had mentioned, we're not here to propose a Gen 6 interconnect limit line. We're not quite sure where the crosstalk and return loss need to fall in, but we just wanted to show how our current connector performs to get a baseline. And we're kind of, again, along the same lines. We expect there may be upgrades needed for all Gen 6 channels, but we'll see as we kind of get more first silicon how it goes. So when we look at our simulations we ran, we focused on two main different topologies, one being a single connector topology, which most of us are familiar with. And this exists of either the right angle or the straddle mount connector. And for our simulation tool, we did use the industry standard non-root complex and root complex package models. We toggled the host board traces between 4 and 14 inches with an impedance of plus or minus 10%. And then we used our OCP NIC targeting the 7 dB of losses defined in the spec. And for all of our simulations here, we ran in both the root complex to non-root complex and non-root complex to root complex directions. And then after that, we wanted to follow up with a cable topology. So as PCIe Gen 6 is kind of removing 4 dB of the insertion loss budget, we're seeing more of our customers ask for a cabled solution. So we wanted to see what different designs we could do there. And for this simulation, we used the same root and non-root complex packages. We used the same family of connectors, but we had to add a vertical SFF TA 1002 connector. And then we toggled the internal cable lengths between 100 millimeters and 900 millimeters. So as a result for this one, we didn't vary the impedance of the NIC and held that consistent. So we look at our single connector topologies, as you can see here. On the left is the image of the straddle mount connector, and then on the bottom is a right angle connector. And in here, we show just a 2D graphic, so the previous slide makes sense of what you're all looking at, and you can see the difference. And then we look at the cable topology, which might be somewhat new to folks here, as it's a little bit different. It's the same root complex with the via and host trace, but then we put a vertical SFF TA 1002 connector, and then an SFF TA 1020 cable assembly. And then this has a direct-to-lead frame cabled receptacle on the other side that would alternate with an OCP NIC. So then for our model simulation setup, we wanted to set up so we could run thousands of different iterations. So we used parameterization models in HFSS. And in here, we concatenated both the Gen 6 package, our own kind of general breakout, PCB trace vias, and the AC caps for the TX pairs. And then on the host board for the cabled solution, it's the same exact setup, but again, adding the vertical connector and then the cable assembly. And then we would then pair this up with the corresponding OCP NIC model that we set up at TE. And this has the PCB trace of the card edge interface, and the via, and then the PCB back to the non-root complex package. And then for all of our simulations, we did include crosstalk with 3 near-end aggressors and 2 far-end. So for all of the simulations we did run, we got a specific detailed report out for those who are familiar with the CSIM simulation tool. And from here, we can pull out the eye height and eye width of all the different eyes. And we primarily focus on the top eye height and top eye width, and then the total insertion loss of the channel. And with this, we are looking for a pass of a 6 millivolt top eye height and a 0.1 UI of a top eye width, and sub 32 dB for insertion loss. So then we went through and ran all these simulations, and if you look at the graph above, we kind of tried to summarize a few of the different here. So the graph is a bit dense, but if you look on here, the furthest left column shows the insertion loss of the host board. For this slide, it's a 4-inch trace, so 4-inch with package and trace was about 13.5 dB. And then across the top, you can see the simulation results of both the straddle mount and right angle for the root complex to non-root complex, and their non-root complex to root complex. And in here, a 0% would be a marginal, what we would consider a marginal pass with either a 6 millivolt eye height for eye height or a 0.1 UI for eye width. And you can see at this short host trace, we do see that the limiting factor is the I width, driven by the return loss and crosstalk performance of the connector. And then when we jump up to the 10-inch trace, we see actually slightly better performance in margins. And we have a clean I height passing and some marginal passes on the I width. And we wanted to continue our host board trace length to see where that shift occurred between I width being the driving failing factor and then I height. And with that, we got out to 14 inches. So once we get up to a 14-inch host trace, we do start to push up on the 32 dB limit defined by PCIe SIG. And that's where we start to see I height become the driving factor and I width actually passing with better margin due to the insertion loss being the more driving component of these channels. So following that, once we hit the limit of the insertion loss for a board technology, we wanted to look into a cable topology for simulation. So in this cable topology, because there was the extra metric of an internal cable, we ended up kind of toggling the parameters a little bit differently. So we did continue to vary the host trace length and impedance. So if you look on the second column, that shows the 3 different impedances of the host traces with the standard plus or minus 10%. And then we have across the top the 100 millimeter, 200 millimeter, up through 900 millimeter internal cable. And then the corresponding traces for that being 3 inches, 7 inches, and 9 inches. And this kind of tells a similar story to the single connector topology in the sense of that the one with the small internal cable, low loss, short trace does suffer from the return loss and crosstalk of the interconnect. And we can see that it has marginal passes on the I width. And then we wanted to push it up beyond where we would see failures from an insertion loss perspective. And this one goes up to about 9 inches of trace with 900 millimeters of cable. So I think this kind of provides an alternative solution for those who would need to meet a longer reach on their servers, but can't provide it with the trace length. So we look at kind of what were our conclusions and takeaways from here. So we do feel that the single connector topology using TE's SFFTA 1002 compliant sliver is sufficient for many PCIe Gen 6 channels, and it did pass a wide majority of our channel simulations from between 4 and 14 inches of host trace. And then beyond 14 inches of host trace, one would maybe need to implement a cable topology. And we found with the cable topology, we can reach up to 900 millimeters internally, with including about a 7-inch host trace. And this also would allow folks to put a more flexible OCP NIC placement, so move it up off the board, stack these 2D without a riser card. And then lastly, our current and existing connector seems to show promising performance for PCIe Gen 6 channel and topologies. So I want to invite everyone, as Damien has mentioned, this is a kind of an ongoing topic in the work group, and we're working on defining PCIe Gen 6 requirements for our connector. So I would invite people to join the work group and join our Wednesday meetings so we can have open dialogue. And all of these simulation results were done with TE designed components and then TE breakouts, but we're always looking to have alternative connector and board vendors to give their own sections, and we can come together and provide more simulations. And then if you want to reach out to anybody at TE to learn more about the connectors involved here, I have the product manager and then a link to the page so you can see about our offering of the connectors that are defined in OCP NIC. And then lastly, feel free to join visit the page to see our wiki spec or join the mailing list so you can get the latest updates. So I don't know if anyone has any questions. All right, thank you.